Hello and welcome back to Functional Analysis. And as always, many thanks to all the nice people that support this channel on Steady or PayPal. Today in part 28 we will talk about the spectrum of a bounded operator. This spectrum comes in as a generalization for the eigenvalues of a matrix. For this, please recall when we have a square matrix A, which means we have n rows and n columns, and the entries can come from the complex numbers. Then we are able to talk about the eigenvalues of A. In particular, we call a complex number lambda an eigenvalue if we find a corresponding eigenvector. More concretely, this means there exists a vector x which is not the zero vector, and it fulfills that Ax is equal to lambda x. Or in other words, the matrix multiplication for this vector x is reduced to a scalar multiplication. At this point, it's a good idea to rewrite this equation. For example, we can just bring lambda x to the left hand side by using the identity matrix. Now we have a new matrix that sends this vector x to the zero vector. However, this then means that the kernel of this matrix contains more than just the zero vector. Please recall, in the kernel we find all the vectors that are sent to zero. Of course, we can also see this matrix as a map, so a map that sends a vector x to the vector A minus lambda I x. Now, having the kernel be bigger than the zero space is equivalent to say that this map is not injective. Okay, this might be a good time to refresh your linear algebra knowledge and talk about the rank nullity theorem. It holds for all matrices M, where the important thing is that we have the number n for the columns. This number n is the dimension we have as an input for this map here. And in the following sense, this dimension is conserved. The new dimension we get out on the right hand side is given by the dimension of the range of M. Therefore, this number can't be bigger than n, and in the case it is less, everything else has to go into the kernel of M. In other words, both dimensions have to add up to the original dimension we put in. Now, because this formula connects the range and the kernel, we immediately get for square matrices and this map that injectivity, bijectivity and surjectivity are indeed the same thing. Hence, here we could also say this map is not surjective, or simply the map is not invertible. However, if we leave the finite dimensional case, this rank nullity theorem will not hold anymore. For this reason, we immediately get different possibilities for which the invertibility of this map can fail. Now, for the rest of the video, let X be a complex Banach space. And T from X to X should be a bounded linear operator. To put it in other words, X is the generalization of Cn and T for the matrix A. Therefore, the spectrum of T should be the generalization of the set of all eigenvalues. So it should be a subset of the complex numbers. And usually it's denoted by the lowercase sigma. Now, inside this set sigma t, we have all the complex numbers lambda such that T minus lambda identity is not bijective. Therefore, if we consider a finite dimensional vector space X, we are in this case again and get out the set of all the eigenvalues. However, for the infinite dimensional case, we will see that we can split up this set into three parts. Before we do that, let's also define the so-called resolvent set of T. And this one is denoted by a lowercase rho. The set looks very similar, but now we look at all the complex numbers lambda, where this map is indeed bijective and the inverse is bounded. So in some sense, these are the good points, because there we can invert our bounded operator. Of course, at this point you know a lot of functional analysis, and therefore you see we are working in a Banach space, and therefore we can use the bounded inverse theorem. Which simply means when we have the bijectivity, this immediately follows. So we can just say sigma is the complement set of rho. With this you see why we need to work in Banach spaces, because only there we get out the inverses as bounded operators. And we work with complex vector spaces because, as we will later see, the spectrum gives us more information in this case. However, of course, all the definitions here also work with real vector spaces when you substitute C with R. Knowing all this, I can show you now how we can split up the set sigma t. The first one is the so-called point spectrum of T. Indeed, this is the only set we have for the finite dimensional case. However, in the infinite dimensional case, we also have a set we call the continuous spectrum and a set we call the residual spectrum. Now, from the discussion above, you might already guess that we can split up the bijectivity here into injectivity and surjectivity. In fact, that's what we can do, and in the case that this operator is not injective, we define the point spectrum of T. Please recall, we learned above that not injective means this operator has a non-trivial kernel, which means we have eigenvectors. In this sense, these points are indeed the classical eigenvalues. Okay, now you should see, to get a disjoint union, we also have to include the injectivity here. So in this sense we could actually do it, but it turns out we can distinguish the points even more. Now, not surjective simply means that the range of the operator is not the whole space X. However, it would be a nice property to have almost the space X. And this should mean that the closure of this set is X. Now, these points lambda form the continuous spectrum by definition. Both names are chosen in this way because for important examples, the point spectrum consists of individual points in C and the continuous spectrum forms whole intervals. This also explains the last name, the residual spectrum just gets all other points. Here the operator is injective but not surjective, and even the closure of the range is not X. Here I can tell you, for the property that the closure is the whole set X, we simply say the range lies dense in X. Later you will see that for many important examples the last set is indeed empty. This is not always the case, but for these examples we only have to deal with these two sets here. Okay, then let's use the next video to look at some examples. Therefore, I hope I see you there and have a nice day. Bye!